In this problem, we'll be applying Gauss's law to a continuous charge distribution to determine electric fields, and we'll see how Gauss's law allows us to exploit symmetry so we can bypass performing any difficult integrals. Let's take a look at the problem statement. In this situation, we have a charge in the center of a spherically charged shell. We're not told either of these charges, and we're asked to find out how much charge is in the shell. We're also told the electric field as a function of distance. We have a graph of that. We can use that information to help us with this problem. So we're looking for the charge in the shell, and the approach here will be to use Gauss's law. Let me just reiterate what Gauss's law is and why it's useful. Gauss's law is a statement about the amount of electric field coming through a surface. And it says that if you integrate the field vector over some closed surface, this circle indicates that you're performing a closed integral, that's going to equal, it only depends on how much charge is inside the surface divided by a constant. What's remarkable about this theorem is that this integral, no matter what surface you choose, only depends on how much charge is inside. It doesn't matter how the charge is distributed or anything. Not only that, it doesn't matter how much charge is outside the surface. So it's kind of remarkable in that before we found fields by using the charges of all the different regions and distributions and doing integrals. And this theorem says that actually, if you take the integral over some particularly closed surface, then all that matters is what's inside. Now, why this is useful is that it's actually always true regardless of what the surface is. But it's useful whenever you have a surface or whenever you have a situation where it has some symmetry. Because then you have symmetry, you can actually pull this e outside the integral. And what's left is e times an area, which equals this value. So the electric field is just going to be this guy divided by the area. And that avoids having to perform any difficult integrals. All you have to do is just find out what the area of the surface is. Let's see how it's useful in this problem. So I'm going to redraw this picture down here. And so I'm going to draw the center at the, the charge at the very center of the sphere. And then we have the charged shell outside. And say we want to find out the electric field at this distance r right here. Okay, so I want to find out what is the field at that particular point. Now the way to use Gauss's law is, well, there's certainly a high degree of symmetry here. It's radially symmetric. So we expect that the electric field will only point in the radial direction because angularly everything looks the same. So you can't have components in angular directions like that. So if the electric field points radially, I'm going to draw a surface that respects that symmetry. And this surface is known as the Gaussian surface. And it's the surface you integrate over in this formula. So this is my surface. It's also a sphere. In other words, it's a ball instead of a charged ball. And if you notice, in this case, the electric field points radially. And also this dA, which is known as the surface normal. And that's the vector that points perpendicular to the surface wherever you are on the Gaussian surface. Also points radially because this is a ball. So everywhere along the surface you have electric field and the surface normal pointing parallel. Now why is that useful? That's useful because now when you perform this integral, the dot product of two parallel vectors is just equal to the product of the magnitudes. So this just equals EdA. So you avoid having to worry about the vectors. All you have to worry about now is the magnitudes. And then beyond that, the electric field is going to be the same everywhere on the surface because it's symmetric everywhere in the angular direction. So you expect the field magnitude to be the same. Because the magnitude is the same, you can actually bring it out of the integral. In other words, this is a constant everywhere on the surface. I can take it out of the integral. And what I'm left with is just the integral over dA, which is just the area. And then all this depends on is the charge inside of the Gaussian surface. All it depends on is that charge at the very center, which I call the Q center. It didn't matter at all what's outside. And so finally, if you do this, the area of this Gaussian surface, and importantly, this is the area of the Gaussian surface over which you're integrating, not the area of any other charges, just the surface you drew. So that's going to be 4 pi r squared because it's a sphere, and the surface area of a sphere is 4 pi r squared. So this is just going to equal the charge at the center divided by 4 pi r squared times epsilon naught. And that tells us that the field magnitude basically just equals the Coulomb constant, which is this 4 pi epsilon naught, times the charge of the center divided by the radial distance. Right, so this theorem is remarkable in that we were able to find the electric field inside of this without even having to think about the charged shell at all. We didn't have to think about what fields that provided. All those field magnitudes end up canceling. All that matters is what's inside of the shell. Okay, so now that we have this, how are we going to proceed? What we're looking for here is, we're looking ultimately for the Q in the shell. The intermediate step will be to find the Q at the center and then redo Gauss's law outside. So I'm going to try to find Q center here. How can we use this graph? Well, we know that we can find out what the electric field is at various distances. So what we're going to do is plug in a distance and the corresponding electric field at that distance to find out Q center. Let me just say a few words about this graph. So something kind of funky happens right here where you have a discontinuous jump. And what that's indicating is that at this point you have a continuous electric field. So at a distance of 1, you have an electric field of 10 to the 10 to the 7. And then it kind of decreases. But at this point it goes down to 0. What happens is that that's actually inside of the shell. The shell is metallic, and electric fields cannot exist inside of conducting surfaces. So that indicates that this is actually how thick your shell is. It's about 0.5 centimeters. And so the shell starts at 2.5 centimeters and extends out to 3 centimeters. And then after that, this is the electric field outside of the shell. So if we're going to use a value from this graph, we're only looking inside of the shell. So we can only use these values, because this is where the shell begins. So in particular, we can use this value right here, which says that at 2.5 centimeters, the field is 2 times 10 to the 7. So the electric field is 2 times 10 to the 7. And if I plug in a value of 2.5 centimeters for the radius, well, then if I solve that for Q center, I'll find that the center charge has to be equal to 1.39 microcoulombs. Okay, so that's the charge at the center. Now, how can this help us? Now, the second step we're going to do is actually do the exact same process, finding the electric field outside of this entire charged shell. In other words, we're going to repeat Gauss's law, but instead of using a Gaussian surface that's smaller than this charged shell, we're going to use one that's bigger. I want you guys to do that on your own. So you're going to set up an integral. It looks just like this, but it's going to be using a Gaussian surface outside, and then find the appropriate enclosed charge, set up the electric flux equals the enclosed charge divided by epsilon naught, and then we'll compare our answers and proceed from there. Okay, so the next step is to find the charge on the conducting shell, which we're going to again use Gauss's law. Let me just indicate that the shell does have some thickness by drawing the physical thickness of the shell. And what we're going to do is, outside of the shell, we're going to use a Gaussian surface, which I'll define. You can make it as big as you want, so let's just use it out here. As long as it's outside the surface, because that's where we're looking for the electric field, outside of both the shell and the charge in the center. And we're going to say that the radius of this guy, let's call it again R. If we proceed using Gauss's law, we're going to have the exact same expression for the flux because it's the same geometry. The only thing that changes now is we have a different enclosed charge. So we're going to have the same expression for the electric field after carrying all this out. We're going to have E over the charge enclosed divided by 4 pi r squared times epsilon naught. The only thing that's going to change is now the enclosed charge is not going to be just the charge of the center. It also includes this charge on the shell. So the enclosed charge is going to be the charge of the center, which we do know, we have a value for that, plus the charge on the shell. And of course, you're going to divide by r squared and multiply by the Coulomb constant. All right, so now we can do the same thing we did before. We have everything in this problem. We can find E and R by looking at the graph. And then we can just solve for the Q shell. So we do want to use the fields indicated on the graph that are outside of the shell. And we indicated earlier that this was a shell. So these are the fields that correspond to regions outside of the shell. We can, in particular, use the field at r equals 3 centimeters, which is 8 times 10 to the 7. So plugging in 8 times 10 to the 7 here for the field value. Q center is 1.39 times 10 to the minus 6 coulombs. Q shell we're looking for. And then KE, you can get that value. And we're dividing by r squared, which we're looking at 3 centimeters. So it's 0.03 squared. And then so solving this, you find that the charge on the shell equals 6.6 microcoulombs. So it's pretty straightforward. And look how powerful Gauss's law is, that it allows us to find fields in various regions without having to perform any integrals. So even though this is a continuous charge distribution, we did no integration whatsoever. And that exploits the fact that this situation has a lot of symmetry. Now, that's the answer to the problem that was being posed, but I want to ask you guys one more question. So we have this shell that has a particular thickness to it, and it's a conductor. And for conductors, all the charge on the shell, on any conductor, always resides at the surfaces. So for this shell, you're going to have the charge can only exist on the inside surface or the outside surface. The question I have for you is, what is the charge on the inside surface? And if you think about it carefully, maybe just do a quick Gauss's law calculation. Determine what the charge is on the inside surface, and you may not have to do any mathematics at all. So take a minute, look at that, and we'll come back and compare our answers. Now, if we're asked to find the charge on the inside surface of the spherical shell, then we just kind of draw a Gaussian surface. And I want to draw the Gaussian surface so that it's actually inside the shell itself. In other words, between the inside and outside surfaces. And that Gaussian surface, if you draw it all the way around, and again, applying Gauss's law is going to be the exact same formula because you've got the same geometry here. Applying that, you're going to get to this part right here. You're going to have electric field equals some enclosed charge divided by this constant here. Now, the enclosed charge is everything inside the Gaussian surface. This time, the Gaussian surface includes the charge of the center, and it includes the inside surface. And we also know that the field inside that is going to be 0 because it's a conductor. So we have the left-hand side of this equals 0, and that means that 0 has to equal the enclosed charge, the total enclosed charge. Well, the enclosed charge is consisting of the charge of the center and the inside shell surface. So that tells us that if those have to add up to 0, whatever charge is in the shell has to cancel out what is in the center. In other words, the charge on the inner shell, or the inner surface of the shell, has to be negative 1.39 microcoulombs. And that way, the total enclosed charge within that Gaussian surface is 0. And that makes the electric field equal to 0. So I'm going to go ahead and stop here, and we'll take a look at the summary because we've done quite a bit here. In this problem, we were given a point charge and a charged shell, and we're asked to find the charge on the shell. First, we use Gauss's law to find an expression for the electric field inside of the shell as a function of radial distance. We then determine the point charge using the given field values from the graph of field versus radial distance. Then we use Gauss's law again to find an expression for the field outside the shell. And then finally, we determine the charge in the shell using again the electric field values from the graph. So I hope this is a good example of how Gauss's law can be very useful for problems to find electric fields involving a lot of symmetry. If you have any comments or questions, please leave them on the link accompanying the video, and we'll see you next time.